Greetings, building science enthusiasts, and welcome back to the Building Science Podcast. Today's episode is brought to you by Aprilaire, the trusted leader in indoor quality solutions. Through their understanding of consumer needs for indoor air quality and HVAC channel expertise, they help home builders leverage the full value and benefits of healthy home solutions. They provide multiple products for variable applications and budgets while meeting consumer and builder demand for indoor air quality improvement. And we've incorporated Aprilaire products into our designs for years because they provide real value for engineered systems. For their full product line, check out aprilaire.com/BSP. That's air with an E. Whatever your favorite way to access the internet besides this podcast, aprilaire.com is the first step towards a healthier home. Now sit back, relax, open your mind, and enjoy the rest of the episode.
Welcome to this. Welcome to the
Building Science
Building Science
Podcast.
Welcome to the Building Science Podcast.
bringing the human factor to architecture and design.
Brought to you by Positive Energy in Austin, Texas.
Feeling good, John?
I'm ready to go. Let's do this.
Okay, hello and welcome back, everybody. Welcome back to the Building Science Podcast. I'm Christoph Irwin with Positive Energy, and I'm here once again with my trusty producer, Miguel. La la la! The singing Miguel. And today we are going to be talking about air filtration, probably one of the most important topics that you don't know enough about. We have on the line with us John Blomer. He's the Director of Engineering at Aprilaire. Please say hello, John.
Hey, everybody.
All right, so you'll be hearing from him shortly. I just want to just jump into the topic briefly. I mean, I think we all have heard about the fishbowl strategy, which is us. We are the fish. We live inside indoor environments. That's the fishbowl. And in that fishbowl, we are immersed in a fluid. We are immersed in air, which is a compressible fluid, but a fluid nonetheless. And in that air are all sorts of things. And that's the topic of another podcast. But I mean, just to give you a hint of the richness here, even just the ways to classify them, you know, whether we classify them by source or origin or their chemical composition or the state of matter, it just, when you start talking about what's in the fishbowl with you, it goes on. And, you know, the short answer is particles, gases, and living creatures. And, you know, we have all kinds of names like aerosols, dusts, mists, smoke, fog, fumes, smog, vapors, colloids. You know, this is a very big topic, but when it comes right down to it, so one of the most basic and useful things you can do to make the air quality, let's switch from fishbowl to air now, to make the air quality in the room around you better is to capture pollutants in the air. And this brings us to filtration. Particulate capture is a really big deal. As I bet we'll talk about, when you're capturing a particle, you're also capturing gas phase pollutants because they are also often stuck to those particles. John, basically I said who you were and where you work. Would you like to tell our listeners anything more about your role there at Aprilaire or what you do?
Yeah, I'm responsible for all our products at Aprilaire. Aprilaire is an indoor air quality product, so air filtration, although one of the areas we started in, we do everything from humidity control to temperature control, ventilation, and air filtration. So, and mostly focused on residential homes.
Fantastic. That is great. And as you know, it's a fantastic time to be in the air quality industry. I mean, you talk about someone being on the wrong side of history, which is somehow a term I've been hearing a lot recently. The people in the built world that are still insistent that it is mainly a visual spatial economic situation and they're not paying attention to the quality of the indoor environment, they are probably, their days are numbered with that perspective. So today we're talking about air. And there's a few important ideas we want to do to kind of frame the topic. And I guess, John, we'll just start with, elaborating on why it's important to filter the air or capture particles. Could you touch in on some of those ideas? Why is it important?
Well, if we go back to once we started doing HVAC, we all had our cheap little air filters that really were there to protect the equipment. And when we had houses that, leaked like barns and we really didn't care, that was fine. But as we're doing a great job of creating these energy efficient homes, and really my phrase is, living in plastic bags now.
Yeah. Or insulated Tupperware box.
You
is
got
what
it.
I've heard.
It's becoming more and more important. So the basic need started out with just protecting your HVAC equipment, but now it's becoming more about catching pollens and spores and dusts and viruses and really just helping clean that fishbowl that we're all living in.
Yeah, here.
Yeah.
So what might be in the air? What might we be trapping?
Well, the typical things would be your pollens and spores. It's fall, it's spring, flowers are blooming. But then you got
Trees,
yeah.
grasses.
Yeah, it's that time of year, and then you got things that you do inside your house. You cook, you run your vacuum cleaner. Talk about gross things like your skin falling off and dust mites. But we all just live in this naturally occurring particle world, anyways. And outside it blows by us and isn't concentrated. But once you go inside, it gets concentrated. And
it builds up.
And ventilation's a part of it. But even when you bring in that outdoor air, if you have something as simple as allergy, if it's not filtered, it can aggravate your condition.
Yeah, and one of the interesting things, thinking about, I love that you brought up sort of the history of filters as being there to protect the heat exchange coils, heat exchange surfaces. Another thing that's always been sort of historically present that just astounds me that no one says, wait a minute about it. Like, wait a minute, which is that we really only filter our air when it's either too hot or too cold. I mean, typically that's the case.
It's very much the case, and we and other people have products that, will turn on the fan to make sure you're running the fan more than just heat and cool.
Oh, fantastic.
Yeah.
So I mean, like you burn toast and you can ventilate suddenly or something like that?
You got it. Or you're feeling the allergies coming on, you can turn your fan on for 24 hours and help clean your air outside. Because at that time, the house is probably a better spot for you than going out and working in the garden.
Yeah, that's true. Right? So here in Austin, besides being the live music capital of the world, its lesser known claim to infamy is the allergy capital of the world. I don't know if of the world, but holy moly, there's so many allergy sufferers, even in our own office. And when you sit down with a client and you say, how would you like to have your home be an allergy-free zone? Really get some attention. Yeah. And so to do that, we capture these particles, right? And we're going to be talking a lot about that. But, well, the indoor air can be worse in terms of concentration of pollutants. Do you have a sense of how much worse?
Off the top of my head, the EPA's done studies and, 5-10% worse. It really depends upon where you live and how your house is ventilated. If you're in LA living next to the freeway, it's a lot different than, central Nebraska.
That's a good point.
But it's... There's many studies out there by the EPA that shows the indoor concentrations being much higher than outdoor levels.
And I was thinking about some of the other things that are in the air, right? So that we're kind of crazy allergic to. Dust mite feces is one of them, and desiccated cockroaches. They break down into this material called chitin, which looks like chitin, CHITIN. Turns out we're not meant to be breathing that stuff. Yeah, and then there's a whole host of things. When it comes to filtration, you and I were talking before the show, and this is the Building Science Podcast, which means systems thinking is part of this. So filtration is indeed part of a system. What else is in that system?
Well, again, the way we look at a house is it is truly a system. So, we also consider, the building structure and how it's done. So you have things like, for comfort, something like humidity helps you. You have too much or too little. If you have too much, you can have cause damage to a building structure. You have too little, you can cause damage to a building structure. But if you sit in the middle, people are happy, buildings are happy. So you got things like humidity, temperature, we all know, and then you got filtration, and then you just have fresh air. Because even though it's filtered, it may be stagnant, and then you got the chemicals in there too. So it's truly a system, and it's a good approach to talk about it because it's not one piece solves everything.
So maybe you could just walk us through the air's journey from let's say your home, and you're in your living room. There's the air around you, and it leaves the vicinity of the space around you on the couch, let's say, and it leaves there and it goes somewhere and it comes back filtered. Could you just briefly run through that? Like, where is it going from?
Well, going to the nastiness, the skin particle leaves your body and fell over on the sofa and the dust poofed up and your wife's running the vacuum. So you stirred up this mess all over your house.
Yeah. It might not be visible, right? I mean, it might be, but chances are it's not.
It's not. The bigger particles are the ones you see, when the sunlight's coming through the window, and those typically fall back to the floor and get kicked up when the kids run through the house. The smaller particles stay airborne, and they're actually what gets sucked more down into the filter. They're also the particles you want to remove because they're the ones that go deep into your lungs when you're breathing. And so, you got the HVAC system running, and it's pulling air from the returns, creating that nice flow. And then it goes through the filter, and depending upon the filter's efficiencies, how much you're removing from the air, then it comes back out through the system. And so if you even install a good air filter from the beginning, things like your ducts stay clean because the supply ducts stay clean, your coils stay clean from the beginning. Your return duct might get dirty, but everything in there is getting captured by the filter anyways.
Or you could do a filter grill and your return duct would probably stay clean.
You could put it right there at the filter. That would work too. And again, if someone's really sensitive, a portable helps. It just helps clean the air even more. If you're, highly allergenic and you want to put a portable in your bedroom at night, it definitely keeps that room even better than the whole house. The benefit of the whole house method, it's same as temperature, is the more I can stir your house, the more I can make everything equal, the more comfortable you are throughout the house. If I only heat one room of your house, that room might be comfortable, but might be a little cooler or a little hotter on the other side of the house.
Yeah, well said. Yeah, and that's good duct design and good diffuser selection.
Yep.
Again, another rich topic, something people don't talk about. And, so your story, basically the air gets sucked out of the room. It goes, through a grill, through a return duct, boom, it hits the filter. And that's where we're going to focus today. But the interesting thing is that even in just that little, let's go forward. It goes past the filter. It goes through the heat exchanger, the furnace or the air conditioner or both. And then it goes through a supply plenum and then back into the room through a supply duct and a diffuser. One of the spots, when I do consulting for air quality issues that is pretty common is where the return grill, it's typically a ceiling return grill or often a ceiling return grill. And at the back side of the sheetrock, which is the bottom of the layer of insulation that's all around your return duct, there's not a good seal sometimes between the return duct or return plenum and the sheetrock, and those little particles, they kind of filter down through the layers of insulation. And return means it's sucking air, and so it sucks them right in. And fortunately, it gets into the filter, but it's potentially a constant pollutant source, particle source for the filters. Yeah.
I mean, it's like every other duct design and application is, if you have holes, air is not going where it's supposed to go.
Yeah.
That's exactly right. So it's important to seal your ducts and to make sure things are nice and tight. And, when you get to the filter, even the filter is inside its housing nice and tight.
Yeah, when I take a deep breath, all the air went through my nose or mouth. I guess a tiny bit maybe through my eustachian tube or something. But, it went from outside to inside. It didn't come, through my leg. And, our bodies are evidencing good strategy. We want to know where the air comes from, and we want to make sure it gets where we want it. This is what we really want to dig into now. The business end of the whole cycle, and it is a cycle. You're pulling air out, you're taking it across a filter, which is a particulate capture machine, maybe no moving parts, but a machine nonetheless. And then it goes back into the space and comes around for a second lap. So let's talk about that filter as a machine. What are some of the terms and parts of a filter?
Yeah, let me start with different technologies. There's really two main topics. One is a filter, as we all know it, a media membrane that you're sucking air through. And then there's the electrostatic air cleaners, which are basically a charged plate that attract particles.
Mm-hmm.
And it's kind of like why your TV screen gets dust all over it.
Well, there's really a one before pleated media or filter media. They have those fiber ones. I mean, I hope they're going out of fashion.
They were the fiberglass ones that we all bought in the 60s and 70s, and those were there to keep the birds from flying into the air handler and getting into the blower.
Yeah, and they only work when they're completely clogged, pretty much completely clogged.
You got it, right. Yeah.
So do you know, are those, you're in the industry. I guess they're still for sale, right? Are they?
You could probably go to some cheap retail outlet and get them, but, you just walk around the Menards or, any retail outlet, and they're a hard thing to find.
No good.
I mean, they might sit on someone's shelf, but I think they're kind of a hard thing to find.
We can focus on filter media, like the paper. Is it a paper?
It's kind of it comes in different phases, different types. Like our older technology was a, kind of a glass paper. It had fiberglass media,
Really?
woven one. It made in the same processes as a paper making machine.
Really?
Yeah.
But it was made of glass.
But that was the main fibers in it. Yep.
Uh-huh.
And the newer.
And this is the media that goes into pleated media filters. When you hear pleated media, is this what you're referring to?
Yeah, that's kind of the older technology. What's changed is we've started to use more synthetic fibers, polypropylenes, polyethylenes, and they're kind of woven, and it allows for less resistance, more capture, higher efficiency. So the technology has changed. Today, if you go into your retail store, your HVAC supplier, you'll probably more likely run into a synthetic media than you will run into a glass media.
So a synthetic woven media.
Yeah.
And so you're saying that it's some sort of polyolefin, I imagine, some sort of molecular chain.
Yeah, they're micron size fibers.
So that means 1 to 2 microns or 1 micron in diameter?
Yeah, and they're kind of laid down on a sheet, and they might have some type of binding material in them, or they might be bound by a little bit of heat. But when you touch them up, they feel like they look like paper. They're a little more translucent than a paper, and they're a little softer. They get a little more cottony feel to them.
In case listeners aren't aware, when we say micron, what we typically mean is a millionth of a meter, right? And so a hair is 50 to 100 microns. So when he's saying it's micron size.
Yeah, they're not single micron.
They're not single. Okay. Make sure. Thank you for clarifying that. And we will be talking about that microns again. We'll be using that shortly when we talk about particle sizes.
Yeah, they're visible to the eye.
You work for Aprilaire, and just curious about this. I guess let's try to stay as manufacturer neutral as we can, but do different filter manufacturers use different filter media?
Yeah, like I said, some people still use glass and the synthetics, and then the synthetic is a broad term for whatever that manufacturer's recipe is. There'll be different recipes, but they kind of have the same base makeup to them. And with the filter media, you typically are looking like a glass fiber or a synthetic.
I guess there's economic decisions in that. There's accessibility decisions in that.
Yeah, you got it all, because in manufacturability decisions, so it gets produced in a great big roll. Picture a paper maker, a 5-foot diameter roll, and it goes through a machine that will pleat it to whatever pleat height and pleat width you have, and then you package it either into a cake box, or in our case, it's a collapsible media, and that's what gets sold. So there's a whole machine that takes the raw paper or media at the one end, and out the backside pops a filter.
Very cool. And how is that roll manufactured? Do you know? I mean, where do you get that, and what's it made of?
The roll is the media, and it's made just like paper. If you've ever been into a paper plant, or it kind of looks like a roll of aluminum. It looks that big, about that wide. And so the media manufacturers will build this media, and it gets used not only in a residential air filter, but it could be in a clean room mask. It's your same stuff that's probably in a surgical mask. Again, different recipes and all those things for their applications. But so the media manufacturers make the media. We buy it in great big rolls to our specific recipe and process it into media and air filters.
Got it. And I've heard the term triboelectric.
Mm-hmm. Yeah, with triboelectric, what it is, basically you have those synthetic medias, and during the manufacturing process, they impart charge onto the media, either by rubbing them together or needling them, or actually putting them in an electronic field. And so the media has an electronic charge to it, and it's kind of like your sock coming out of the dryer. It sticks to a lot of things. So when a particle comes through, it helps pull the particle and hold on to it.
And then that's what you order, is you order this media. And it's had this done to it before you get it. Okay.
Yep.
And then you put it through a machine to pleat it, and everyone's doing that. So what's the next component after filter media?
In our case, we build the whole air cleaner. So you'd have a housing, an HVAC system. It might come on the furnace. Furnaces sometimes come with a 1-inch little slot that they slide the media into. In our case, we're building a 4-inch wide metal housing. And that mounted metal housing gets attached to the furnace, and then the media slides in and out. So we produce the whole thing. In the case of the air cleaner housings up here, again, it's very highly automated. We bring in rolls of steel, goes through some elaborate machinery, and out pops a metal can out the backside.
Are they painted? Or are they galvanized? Or
what we make them in different levels. Bottom line is, at minimum, they have to be galvanized because you don't want them rusting. Mm-hmm. But then, we do sell them painted also. Depends upon price point and what the installer contractor is looking for. Galvanized might typically go into a new home construction, where painted units will go into a replacement where people are upgrading equipment and they want it to look nice next to their 20-seer air handler they just bought. So it varies, but that can at least should be galvanized and clear coated.
Okay, so we got the media, we got the chassis. We're also pleating the media. Everyone's pleating the media these days. Can you explain to our listeners just what's the basic logic behind pleating or folding the media?
So the reason you pleat and fold a media is you're really trying to minimize air resistance. So if I breathe through a flat piece of media, try to push something through a flat piece, it's harder than if I have a really big piece. It's just an area equation. So the more area you can put into a filter, the lower the pressure drop. Now there's a lot of science behind it, in fact, because where the pleat folds, you get the little tip on the top of the pleat, you'll get pleat losses. So that's basically a no airflow place. So you have to balance pleat spacing with pleat height, with media area, with resistance of the media to get the right properties you want out of each filter.
Different manufacturers probably have different recipes for that.
You got the base resistance of the media, and then how big, then the deeper you make them, they typically have less pressure drop, and then they can hold more dust, so they last longer.
Yeah, we'll talk about that. I want to just expand just briefly on pressure drop because that's such an important concept. I mean, I was about to say it's where the rubber meets the road for a mechanical engineer like me. And it's interesting. One of the metaphors that I think gets some traction is to talk about tires on a car. Like people could buy a very fancy, like a Tesla or let's say you have a Prius and you just want to get the best mileage you can possibly get. Well, one of the determinants of your gas mileage is the resistance of the rolling resistance, let's say, of the tires on the road. And so if you buy a Prius and you fail to account for properly inflating the tires, well, then you're going to have higher rolling resistance. You're not going to get the mileage. And so when it comes to a designer, this static pressure, this drop in pressure from the air handler through the supply plenum, through the house, through the return plenum and back, that whole drop, that's the pressure drop we want to make as small as possible, which is very much like reducing the rolling resistance of a car or of a car tire. And we make it small we would like to make it small by doing good air distribution design, but we've talked about that before, as you know, John. Often duct systems aren't designed, they're just installed. But two of the most unavoidable areas to have pressure drop because they're both critical to the system. One is the air handler itself, the heat exchanger, like the air conditioning coil or the furnace heat exchanger. But then the filter, that's another one. One of the reasons that we're talking to you is because I met you at a trade show, because we spec your air filters because they have very low pressure drop. And this must get into that magic we just talked about, pleat loss at the tip and pleat spacing and how you've chosen it. So thank you for letting me digress for a minute about that. So filter bypass, actually, when we met at AHR a couple of years ago, I was very skeptical that one of the ways that you managed to get your pressure drop very low across the filter was that I wondered whether or not some of the air was actually not going across the filter, and that's called filter bypass. And you assured me, and you actually showed me how you're preventing filter bypass. Could you describe that?
Yeah, so filter bypass, like it sounds, is air squirts somehow around the filter.
Which you don't
want, because that's not getting any cleaning done. And you're right. If I want the lowest pressure drop, I don't put the filter in.
If I want the best, I put a plastic sheet across it. No dirt gets through.
Brick wall works great. With our designs, the filter goes right up against the housing, and it bends over, and it guarantees a seal. You cannot put our filter in wrong and allow bypass. When you look at something like a cake box filter, and we've all seen them, it's cardboard framed filter. The media might be going up against the cardboard, but then you take this cardboard filter that's been on someone's truck or thrown in the shopping cart at Menards, and it's got dents and bangs and everything else on it, and then you slide it in a slot that may be too big or too loose, and it's really hard to guarantee that you're not getting bypass around it. And so that's the beauty of one of our designs is that we don't have that cardboard box. The other thing that kind of sets us apart is when we talk about performance of our filters, it's inside our housings and it's the whole air cleaner. Versus a filter manufacturer they will rate their filter, but again, when you slide it in that box, who knows what it's really doing because it might have gotten damaged and ripped and everything else.
Yeah.
And so our advice is if you can look in your ductwork somehow, and if you can see light around that filter, it's not doing its job.
Because the air is going to not going to force its way through a filter if it could just go
It's
around.
going to take like the rest of us, we take the easiest way out.
Let's not try to stay on it too long, but could you go through the basic ways that particles are captured by a filter?
Yeah, I mean, one method is what it's called sieving, and it's just like it sounds. You pour your spaghetti into the strainer, and the spaghetti stays behind, and the water goes on
There you
through,
go.
right?
Okay.
So a small particle can't go between the fibers that we talked about with the non-wovens.
What is the spacing between those fibers, roughly?
It's submicron size. Again, it's a random laying down of fibers.
Oh, interesting.
Yeah, so it's submicron. It's some spots might be a little bigger, but most of it's a fiber set on a fiber. So that's the first mechanism. Another one is called interception. So basically, a particle's flying through the air and it runs right into that fiber and it sticks to it and impales itself right onto it.
Interception reminds me of football. So the particle was trying to make it by the fiber, but the fiber reached out and
You
grabbed
ran
it.
into the linebacker.
Okay, and what's after interception?
And then you got kind of an inertial impact, which is kind of similar to interception, where it just
But it's more like you ran right into it.
Yes, you got it. And then you got, like I talked about the electrostatic attraction. So you could have particles that have different charge. You can have the fibers have one charge and particles have another, and they're magnets on themselves.
And it'll hold that charge. The fiber will hold that charge for its lifetime. Does the airflow going across it dissipate it or hold it? Or
No, they hold very well. We've tested them for years of use, and they don't really lose their charge. Yeah, you can take an electrostatic charged media, and in Europe they'll actually douse them in alcohol and take all the charge off, and it'll drop a couple. It might drop 1 or 2 MERV ratings.
Why would they douse it in alcohol?
Because they're trying to remove the charge. There's a theory that it's kind of what you brought up is, well, that thing loses charge over time, so it's not a good filter.
Oh, so they want to disable that mechanism and see how it works.
Exactly. We've done enough testing where we've put these products in the field for years, and they may leave our building in a MERV 11 or 13, which we'll talk about later, and they come back at a MERV 11 and 13 because they might lose a little charge, but they're also gaining some efficiency because of all the dust they're holding. So the filter's still working as good as it went out.
Just to be clear, I mean, you mentioned this early on. We talked about the 3 types of filters, basically fibrous media, paper or pleated media, and then electrostatic. I spent many, many years, and I still go in attics occasionally with clients, and I see electrostatic filters up there. It was several years in before I saw an electrostatic filter that hadn't been disabled, hadn't like a true electrostatic in terms of there's a power cord coming to it. That's not what you're referring to when you're talking about electrostatic attraction. You're saying the media has an inherent electrostatic charge, correct?
Absolutely. Yep. It's kind of the static your sock coming out of the dryer. It's got a negative charge on it.
And what's your assessment of the true electrostatic filters? How do they compare to this?
Well, the comparison between the two is an electrostatic filter will have a lower pressure drop because it's wires or something in the airstream.
Yeah,
right.
It's wide open,
and it will have a good initial efficiency. But the moment those wires start to get covered with dust, the efficiency drops off real fast. Where a media type filter might have a higher initial pressure drop, but as it gets older, its pressure drop, its efficiency increases, and so does its pressure drop. So the argument between the two is which would you rather do? Have your air cleaner keep working and get better, or work and not work? So that's kind of if you put the two technologies in a room, that's the debate they'll have between themselves.
Yeah, and just to elaborate for people listening to understand, basically, I get to pick an air handler, and I get to design for different pressure drops. And typically, air handlers are designed for around a half an inch of water column. So that's 0.5, and they use IWC, which I like to think in pascals. That's like 125 pascals, a little less than that, but 125 pascals of pressure is kind of like my pressure budget. Some of these manufacturers like Mitsubishi that make these VRF systems, they will only give you 0.2, or even some of the systems 0.12 inches of water column, but 0.2 is more common. And so instead of 125 Pascal budget, I have like a 50 Pascal budget, and that's all I have to work with. But the duct system scrubs away from my budget. The return grill scrubs away from the budget. Of course, the air conditioning coil itself scrubs a lot away, and the filter. And so you can see as a designer, man, you want to keep it as small as you can everywhere you can. And the last thing is, and you know this stuff, I'm sure, John, but that moving air takes energy. And the less resistance to moving that air, the lower the energy use, needed to cause that to happen. And this is a life of the home, a life of the system kind of thing. And it's why one of my pet peeves is that homeowners, it's you homeowners out there, they get all concerned about which air conditioner to buy when, that lasts a long time, but you do change it out over time. And you're not going to, the house wasn't built and then torn down with the same air conditioner. Maybe sometimes, but the same duct system almost always, right? So when in doubt, spend more money on your air distribution system and its design than fretting about, should I do the SEER 16 or the SEER 18 or the SEER 21? It's kind of like a bait and switch tactic. They've just switched you to think about something that's less important. But your filters, so I just gave some numbers, right? So let's say I have a 1/2 inch, or you can actually have 0.8 inches of water column, which is 200 pascals. It's easier to think in pascals somehow for me. But so let's say I have 0.5 inches of water column, 125 pascals. A typical filter, like a MERV 13, which we'll talk about MERV coming up. Do you know off the top of your head roughly what's the inches of water column drop or the pascals drop on that?
We typically rate our airflows at about 2,000 CFM airflow. That's kind of where we publish our performance numbers, which is kind of at the upper end of performance or airflow.
Okay.
Yep. So everything in the real world is less than this, but our MERV 11 medias are typically around 0.14 inches. 0.14.
0.14. Okay.
And our MERV 13s are around 0.16.
That's amazing.
Yeah, and then you get some of our models like that are bigger. So again, we're increasing surface size, and we can get down to 0.08 at 2,000 CFM. It's just a bigger air cleaner. We do have a wide range of MERV ratings and sizes, but we're below 0.18 on all those.
Yeah, that's amazing. And most of the people listening probably don't know that that's an amazing number, right? So 0.08 is like 20 Pascal and 0.18 is like 40 Pascal. And I can look up other filters that are, they kind of crack me up because they'll be a 1/2 inch of water column. It's like, well, excuse me, that was my whole budget.
What everyone's used to is the 1 inch filter. And those the best ones are doing 1/4 of an inch. You can convert that to pascals.
Yeah.
And that's
60.
brand new and some of the best. And you're right, they do go up to 1/2 inch.
Yeah, and it's crazy. And so what that means is as long as the air conditioner exists, because keep in mind, you can change out the air conditioning equipment itself, but it's going to suck air through a filter, and that filter is connected to a duct system. And if it's trying hard to suck, I mean, think about like what was it? Wendy's. You can get a Frosty, and they'll give you a larger diameter straw. It's you don't want the air conditioner constantly struggling to move air through itself, right? What does it do? That's what it constantly wants to do, is move air. So you want to make it easy. Okay, minor rant there. All right, so that was electrostatic attraction, and I pulled you away. What's the last way that particles would be leaving an airstream?
Another method is sedimentation. So as the particle goes through the filter, it just slows down and gets stuck into the filter. Those will be bigger particles.
That you talked about in the beginning, how the big what's called the coarse particles. Maybe I'll run into that in a minute. But how when you see dust in the sunlight, the big particles are settling to the floor. Those are the big ones, and that could be an example of sedimentation.
Yep.
The dust,
exactly.
The dust falling out. And so just to touch on that, and then we'll talk about MERV. But when we rate particles, for some reason they call it particulate matter, and they use the abbreviation PM. And so PM10 means particles that are 10 microns and smaller. That's coarse particles. And then the famous one that you see on like allergy forecasts is PM 2.5. Those are called the fines. And those are 2.5 microns and smaller. And then the ultra fines, which from what I've been reading, they're the particle diameter of emerging concern. And those are 1 micron and less. And then on all those, when I said 10 microns, 2.5 microns, or 1 microns for coarse, fine, and ultra fine, it's not really the diameter because the particle is not necessarily a ball. I mean, think of like little randomly shaped asteroids, or like you said, skin particles. And so what that number is, like if it's saying 2.5 microns, it's actually referring to the aerodynamic diameter. And what that refers to is it moves through the air as though it is a ball or a sphere of that diameter.
I mean, the other thing to keep in mind is, the 10 micron and greater, you have natural filters. Your nasal hairs capture that kind of stuff. When you get to the 2.5 microns and less, that's what goes deep in your lungs. And that's where the health issue becomes in.
Just to make it really succinct and clear for everybody, when you're capturing a particle, think of like an M&M, where the candy coating on that particle that you're capturing, that candy coating, it is not candy. It is a rich, nasty potpourri of gas molecules, or, VOC molecules or pollutant molecules. So when you trap these 2.5 micron particles deep in your lungs, that's like the M&M, right? It could have been a piece of skin cell that broke up and got very small, but then sorbed into it could be phthalates or bromated flame retardants. So air quality, as you and I know, John, it goes on and on. It's like an endless cavern. Next thing is, we've been alluding to this term MERV, and we're not talking about Merv Griffin, for any of you old enough to know what that might have meant. Talk to us about MERV and how that relates to ASHRAE, John, please.
ASHRAE created the MERV table. It's typically called an ASHRAE 52.2 standard, 52.2. It's minimum efficiency reporting value. And what that means is you take a filter and you test it new and you test it full. And whichever is your lowest value is what you have to report.
Interesting. I always wondered about that. I always kind of, I'll admit, felt slightly irritated. Like, what the heck? Like, why are they saying MERV? Right? What is this minimum efficiency reporting value? It seems like a way to make it as unobvious as possible what it means. Yep. So what it means is you test it new, you test it full, and you report the minimum value. I get it. How is it tested? Or actually, how long has ASHRAE 52 been around?
I think it's been around for a little more than 10 years or so, and it was preceded by 52.1,
okay,
which is kind of an obsolete standard. I don't think anyone tests to it. It's what they used to use when we were worried about birds flying through the air handler.
Okay.
Yeah. And so the way the test runs is it's in a duct. It's a big machine. We have one here in our lab, and it's probably in all together 50, 60 feet long of stainless steel duct. And,
oh my goodness.
It's kind of a loop. It's a big circle, so you're constantly bringing the air through it. And you basically inject dust of aerosol into the duct. And they have a particle counter upstream of a filter that counts the particles. The air goes through the filter. There's a particle counter downstream of the filter. You measure the difference between the two, and you figure out how efficient your filter is. And then what they do.
And so you must be dumping some dirt into this machine.
Yeah, there's an aerosol generator. It's a salt that gets generated into that machine. Very, very controlled environment.
That's very cool. And so what are they dumping in? I mean, I'm always curious. So when they rate it, they're not just going to someone's vacuum cleaner bag and dumping that in, right?
No. It's kind of a salt. Yeah, it's a generator. So the generator creates particles of varying sizes.
Oh, so it's like grinding the salt, or what's it?
Yeah, it's the best way I can describe it is like a salt, but it creates a dust, but it's a known dust with a known characteristic, and known sizes are generated in there. The purpose is to get really a lot of little small ones and a lot of big ones, versus if I were to just dump my vacuum cleaner bag, one day it's full of dog hair and the next day it's full of pollen. So it's just a very controlled dust generator.
Okay, that's interesting. And then it makes particles across a range of sizes, right? But there must be sizes of interest. Like we talked about this PM 2.5, it must make that size.
Yeah, so it makes them down to basically what you're doing is you're scanning sizes from like 0.3 microns up to 10 microns. And then what they do with MERV is they put it into three bins. So they basically break it into that range into three chunks. And then depending upon it's called the E1, E2, and E3 channels. The more efficient you are in the E1, which is the 0.3 to 1 micron size.
The ultra fines.
Yep, the higher your MERV goes. So like a MERV 8 filter is it doesn't have to have any efficiency in an E1 channel, so your microfine, but it has to be greater than 70% efficient in the E3. And E3 is 3 to 10 micron range. Where you go to a MERV 13, it has to be greater than 50% in the E1 channel.
I see. And that is the current recommendation, by the way, isn't it? The MERV 13 ASHRAE.
Depending upon where you live, and what's going on. But there definitely is a push to go up in filter efficiency.
It's fascinating. So you separate it into these three buckets, 0.3 to 1 on E1 and then 3 to 10 on E3. So in between there must be 1 to 3 on E2. Other thing I want to touch on is this word HEPA that's also out there. You hear that a lot when you're talking about filters. HEPA, HEPA. Could you touch on that briefly?
Yeah, so the highest the MERV table goes is to a MERV 16, which is greater than 95% efficient on that channel. So HEPA's into the 99% range.
I see. And what does HEPA stand for?
High efficiency particle arrestor, I think.
If you consult Lord Google, there are rationale being made that, let's say, in sleep zones, in certain environments, it might behoove us to consider HEPA quality filtration. MERV, that MERV 13 is definitely what I've read. And we have a table that you provided, it's probably out of the ASHRAE 52 too, that really does a great job of helping people visualize this MERV 1 to MERV 16.
It was built by engineers for engineers, so it's not a great marketing tool. So if you do go to Home Depots of the world, people have come up with their own, cleaner delivery rate or some other method it's more of a help a consumer understand. The hard part to teach someone about filter is it's not about just MERV. It's about filter efficiency. It's about life of a filter or dust holding capacity, and it's about pressure drop. And you kind of have to balance those things for your needs. For example, you can have a good, what's called a MERV 14 1-inch filter, and it only lasts a month before it plugs up, right? So it had a higher initial pressure drop. It had a great MERV number, but it had poor life. And that's why the extended medias like ours with the deeper boxes, the 4 inches and bigger, they combine the both. So they give you a good low pressure drop. They give you at least a year of life. So they're just a better filter that way.
That's such important information. Thank you. And just to round out this, because it's one of my minor pet peeves, is that MERV is a standard. And I like that you said it's by engineers for engineers, but it is a standard. And what we've had is a company, I believe it's 3M, has their MPR rating. And I don't know what that stands for exactly, but MPR, like a MERV 13 is an MPR of 1500, I think, or 1900. And then there's another manufacturer, Honeywell, has FPR, which filter performance rating is I think what that one stands for. And that one, a MERV 13, would lay an FPR of 10. But the whole thing with MERVs and MPRs and FPRs and all the different numbers, in my opinion, it's a fairly transparent way of making the person picking the thing off the shelf not really clear on what it is, and which number they want. And okay, so John, what a treat, what a pleasure. Wait, before we do that, you get the last word. Anything you want to say?
Just that, we've been in this indoor air quality business for well over 50 years. This is where we live, and it's all residential. So we consider ourselves, indoor air quality, healthy home expert. That's all we're focused on. And I really like the way you phrase it up. It's a system approach. There is not one magic pill for everything. And depending upon where you live and how you live, you might need one or more or multiple products. And, consulting a good expert, whether it's your HVAC builder or some, building science person is very important, because it can be a confusing thing to get the best, most economical answer for your needs.
Well said. That's a great place to end. John, truly a pleasure. I appreciate you taking the time to talk to me and to talk to our audience. And when we have more questions, we will bring you back on. Thank you so much.
Thanks for having me. Appreciate it.